Electricity powers nearly every part of modern life, from the lights in our homes to the devices we rely on every day. Yet for most people, it comes from a system they don't control: utility grids, monthly bills, and rising costs that seem unavoidable. But one individual decided to explore a different approach, testing whether it was possible to generate a consistent flow of electricity over an entire year using a simple system built primarily from PVC pipe and basic mechanical components. But here's the question: can a setup like this actually produce reliable electricity for everyday use? Or does it only work under limited conditions? Let me know your answer in the comments below. The concept behind this experiment is rooted in well-documented scientific principles. According to established research in physics and engineering, electricity can be generated through the conversion of kinetic energy into electrical energy. This is the same principle used in hydroelectric power plants, where flowing water spins turbines to produce electricity. On a smaller scale, similar systems have been used in off-grid environments, particularly in rural areas where access to traditional power infrastructure is limited. According to publicly available renewable energy studies, microhydro systems are capable of generating small but consistent amounts of power when there is a steady source of flowing water. However, efficiency depends on factors such as flow rate, pressure, and system design. The experiment in this case appears to adapt these principles into a compact, enclosed system using PVC pipes as a structural framework for controlling flow and pressure. The setup began with the construction of a looped PVC pipe system designed to allow continuous water movement. Pipes were arranged vertically and horizontally to create a controlled pathway for fluid circulation. A small turbine generator was installed within the system, positioned at a point where water flow would be strongest. The goal was to maximize the transfer of kinetic energy into mechanical rotation, which could then be converted into electricity. Initial assembly required careful attention to detail. Each pipe joint was sealed to prevent leakage, and angles were adjusted to maintain consistent flow. According to documented observations, even slight misalignments in pipe positioning could significantly reduce efficiency. The system relied heavily on gravity and pressure differences, meaning that elevation changes within the setup played a critical role. Once assembled, the system underwent initial testing. Water was introduced, and flow patterns were observed. At first, circulation was inconsistent. In some areas, water moved too slowly, while in others it created turbulence that reduced efficiency. Adjustments were made incrementally, raising certain pipe sections, narrowing others, and repositioning the turbine to capture optimal flow. These early challenges highlight an important principle in energy systems. Efficiency is not determined by a single component, but by how well all components work together. In this case, the PVC pipe structure acted as both a conduit and a control mechanism, guiding water in a way that maximized usable energy output. During the first few days of testing, measurable voltage was detected, confirming that the turbine generator was functioning. However, the output was relatively low and fluctuated depending on flow stability. This led to further refinements, including smoothing the internal surfaces of the pipes to reduce friction and adjusting the inlet design to maintain consistent pressure. One key moment occurred when the flow became stable enough to maintain continuous turbine rotation without interruption. This marked the transition from experimental setup to functional system. From that point forward, data collection became more consistent, allowing for accurate monitoring of performance over time. According to engineering standards, systems like this must account for energy loss at every stage. Friction, turbulence, and mechanical resistance all reduce overall efficiency. In large-scale hydroelectric plants, these losses are minimized through precise engineering and high-quality materials. In a DIY system, however, achieving similar efficiency requires careful design and continuous adjustment. As the experiment progressed, the focus shifted toward long-term performance. Daily readings were recorded, including voltage output, flow rate, and system stability. Environmental factors were also noted, such as temperature changes and water quality, as these could affect performance. Legal considerations also come into play when discussing self-generated electricity. In many jurisdictions, small-scale energy systems for personal use are permitted, provided they do not interfere with public utilities or violate safety regulations. According to regulatory guidelines, connecting a private generation system to the public grid typically requires inspection and approval. One interpretation is that systems used independently, without grid connection, fall within acceptable personal use. Another perspective raised in regulatory discussions is that improper installation could pose risks, particularly if electrical components are not handled correctly. This is for informational purposes only and not legal advice. As testing continued, the system demonstrated gradual improvement. Output became more consistent, and fluctuations decreased as adjustments were refined. However, it became clear that the system's performance depended heavily on maintaining continuous flow. Without movement, electricity generation would stop entirely, reinforcing the principle that energy must come from a sustained external source. This brings attention to a critical limitation. According to the laws of thermodynamics, energy cannot be created from nothing. Any system that generates electricity must rely on an input, whether it is water flow, wind, solar energy, or another external force. In this case, the system depended on maintaining motion within the water loop, which required either an initial energy input or a naturally sustained force, such as gravity. Despite this limitation, the experiment continued into extended testing, with the goal of determining whether the system could operate reliably over weeks and months. Maintenance routines were introduced, including regular inspection of pipe connections, cleaning of internal surfaces, and monitoring of turbine performance. These early stages laid the foundation for a deeper understanding of how small-scale energy systems function in real-world conditions. The combination of simple materials and established scientific principles created a system that, while not perfect, demonstrated measurable results. As the system moved beyond its initial testing phase, the focus shifted toward consistency and long-term stability. Short bursts of electricity generation had already been observed, but the real objective was to determine whether this setup could sustain output over extended periods without constant intervention. Daily monitoring became a critical part of the process. Voltage readings were taken at the same time each day to maintain consistency in data collection. In addition, flow rate within the PVC system was carefully observed, as even minor disruptions in water movement had a direct impact on energy output. Over time, a pattern began to emerge. Stable flow produced stable voltage, while fluctuations in movement led to immediate drops in output. To address this, the system underwent further refinements. The internal layout of the pipes was adjusted to reduce turbulence, which had previously caused uneven pressure distribution. Smooth, uninterrupted flow paths were prioritized, and areas where water slowed down were restructured to maintain continuous movement. These adjustments significantly improved overall performance. Another important development occurred when the homeowner introduced a more controlled entry point for the water. Instead of allowing water to enter the system freely, a regulated inlet was installed to maintain steady pressure. This change reduced sudden spikes and drops in flow, which in turn stabilized the rotation of the turbine. As a result, voltage output became more predictable. Throughout this stage, careful documentation was maintained. According to recorded observations, the system produced small but consistent amounts of electricity once flow conditions were optimized. While the output was not comparable to conventional household electricity sources, it was sufficient to power low-energy devices, such as LED lights or small electronic components. At this point, an important question arises about expectations. Many DIY energy projects are often misunderstood as replacements for full-scale power systems. However, according to engineering standards and renewable energy research, small-scale generation systems are typically designed to supplement energy needs rather than replace them entirely. One interpretation is that systems like this can reduce reliance on external power sources when used strategically. Another perspective raised in technical discussions is that efficiency limitations make it difficult for such setups to scale without significant upgrades in materials and design. As the experiment continued into its second phase of long-term observation, the homeowner introduced scheduled maintenance routines. Every few days, the pipes were inspected for signs of blockage or buildup. Even minor debris accumulation could disrupt flow, leading to decreased performance. Cleaning the system ensured that water movement remained smooth and uninterrupted. The turbine itself also required attention. Over time, mechanical components can experience wear due to continuous motion. Regular checks were conducted to ensure that the turbine blades remained aligned and free of obstruction. Lubrication was applied where necessary to reduce friction and maintain efficiency. Environmental factors also played a role in system performance. Temperature changes affected water density and flow behavior, while external conditions influenced overall stability. During cooler periods, slight variations in output were observed, although the system continued to function within expected ranges. Another key turning point came when the homeowner experimented with slight elevation changes within the system. By increasing the height difference between certain sections of the PVC pipes, gravitational force was enhanced, leading to improved water flow. This adjustment resulted in a noticeable increase in turbine speed and, consequently, higher voltage output. However, these improvements also highlighted a fundamental limitation. While output increased, it still remained within a relatively low range compared to standard electrical systems. This reinforced the understanding that while the system was functional, it was not designed to power an entire household independently. From a legal and safety perspective, the system remained compliant as long as it was used independently and did not interfere with public infrastructure. According to general safety guidelines, electrical components must be handled carefully to avoid hazards such as short circuits or overheating. Ensuring proper insulation and secure connections was essential to maintaining safe operation. This is for informational purposes only and not legal advice. As weeks passed, the system demonstrated a level of reliability that exceeded initial expectations. Continuous operation was maintained with only minor adjustments, and output remained consistent within its operational limits. Data collected over this period showed that the system could function effectively when properly maintained and monitored. One of the most significant observations during this phase was the relationship between input energy and output electricity. The system clearly depended on sustained motion within the water loop. Any interruption in flow resulted in an immediate disruption in electricity generation. This confirmed the principle that energy systems require continuous input to produce consistent output. To further test durability, the homeowner allowed the system to run for extended periods without interruption. This stress testing revealed areas that required reinforcement, particularly in pipe joints and turbine mounts. Strengthening these components improved overall stability and reduced the risk of failure during long-term use. The experiment also provided insights into cost efficiency. Compared to commercial renewable energy systems, the materials used in this setup were relatively inexpensive. PVC pipes, basic fittings, and a small turbine generator represented a low-cost entry point for experimentation. However, the trade-off came in the form of lower efficiency and limited output capacity. As the system approached a full month of operation, the results became clearer. The setup was capable of generating electricity consistently under controlled conditions, but it required careful design, regular maintenance, and realistic expectations regarding performance. Given these observations, do you think systems like this could become a practical way to reduce electricity costs, or are they better suited for small-scale experimentation? Share your thoughts in the comments below. The findings from this stage set the foundation for a deeper evaluation of long-term sustainability, efficiency limits, and real-world applicability. As the experiment moved forward, attention would turn toward extended operation over several months, exploring whether the system could maintain its performance over an entire year. As the system moved beyond the initial weeks and entered long-term operation, the focus shifted toward sustainability over months rather than days. Running a system continuously introduces challenges that are not always visible during short-term testing. Components begin to show wear, environmental factors accumulate, and small inefficiencies can gradually impact performance. During the second and third months, the homeowner maintained a structured observation routine. Voltage output was recorded weekly, while flow consistency was checked every few days. The data showed that while the system continued to function, minor variations in performance began to appear. These were not sudden failures, but gradual shifts, slightly lower output on some days, minor fluctuations in flow, and occasional need for recalibration. One important observation involved internal buildup within the pipes. Even with clean water, small particles and mineral deposits began to form along the inner surfaces. This created additional friction, which reduced flow efficiency over time. To address this, periodic cleaning was introduced as part of the maintenance routine. Once cleaned, the system's performance returned to near original levels, highlighting the importance of regular upkeep. Another factor that influenced long-term performance was mechanical wear in the turbine generator. Continuous rotation over weeks and months led to minor degradation in efficiency. The turbine did not fail, but its performance slightly declined until adjustments and maintenance were applied. Tightening mounts, realigning blades, and ensuring proper lubrication helped restore consistent output. As the experiment approached the 6-month mark, the system had demonstrated that it could operate reliably with ongoing maintenance. However, it also reinforced a key principle. No mechanical system remains efficient without regular care. What initially appeared to be a set-and-forget solution required consistent attention to maintain stability. At this stage, the homeowner conducted a broader evaluation of energy output over time. When averaged across several months, the system produced a small but steady amount of electricity. This output was sufficient for low-energy applications, such as charging small devices or powering basic lighting. However, it remained far below the level required for full household energy needs. This led to a critical analytical point. Claims of free, endless electricity must be understood within the framework of physical laws. According to the principles of energy conservation, a system cannot generate energy without an input source. In this case, the energy came from the movement of water within the system, which itself depended on gravity, pressure differences, or initial input energy. One interpretation is that the system effectively converts existing energy into usable electricity in a controlled and repeatable way. Another perspective raised in engineering discussions is that such systems cannot sustain themselves indefinitely without an external driving force. This distinction is essential when evaluating the realism of similar DIY projects. From a legal standpoint, the system remained within acceptable boundaries as long as it operated independently and did not connect to regulated power infrastructure without approval. According to general regulatory frameworks, personal energy experiments are typically allowed when they do not pose safety risks or interfere with public systems. However, improper installation of electrical components could create hazards, making safety precautions a priority. This is for informational purposes only and not legal advice. As the experiment reached the final phase, approaching a full year of operation, the results painted a clear and balanced picture. The system successfully demonstrated that electricity can be generated using a simple PVC-based setup combined with basic mechanical components. It also showed that consistent output is possible when the system is carefully designed and maintained. At the same time, the limitations became equally clear. The system required continuous input energy, regular maintenance, and realistic expectations. It was not capable of replacing traditional electricity sources, but it served as a functional example of small-scale energy generation in practice. The most significant takeaway from this year-long experiment is not just the electricity generated, but the understanding gained. It highlights how fundamental scientific principles, flow, pressure, motion, and energy conversion, can be applied in practical ways using accessible materials. It also emphasizes the importance of critical thinking when evaluating claims about free energy or unlimited power. Given everything you've seen, here's the final question. Do you think DIY systems like this represent the future of small-scale energy independence, or are they simply useful experiments with limited real-world application? Share your thoughts in the comments below. If you found this breakdown helpful and want more real-world experiments explained in a clear and factual way, make sure to subscribe to the channel and press the bell icon so you don't miss upcoming videos. And don't forget to comment below and tell us what topic you want the next video to cover. Your suggestions help decide what we explore next.